Hello, Calculus. This is your last lesson of Unit 3. So this is Lesson 6 on Taylor and Maclaurin series. So in this lesson, this is going to be really just taking everything that we've been doing this unit and putting that cherry on top and taking everything and really finishing off with let's take what we started with, our Taylor and Maclaurin polynomials, and culminate with Taylor and Maclaurin series. Okay, so here I have screenshotted the definition from your textbook of a Taylor and Maclaurin series. So what you'll see here says if function f has derivatives of all orders at x is equal to c, then the series, and then you have this whole mush. Okay, let's talk about what this actually is. So this piece right here, this yellow that I'm highlighting, that should look very familiar to you. What is that? Well, that just looks like exactly how we started off this unit with Taylor. This is a Taylor polynomial, but the one thing that's different about it, right, is at the end, we keep going. We have that plus dot, dot, dot. So that makes this into a Taylor series, okay? I'm actually going to erase that so it doesn't look as challenging to see. But so that's what our goal is for today is we're going to think about how can we now apply the Taylor and Maclaurin polynomials and make it into a series, okay? So let's go ahead and see. And actually, I'm going to have you pause the video so you can write this down, and then we'll get started. Okay, here we go. All right, so we are going to begin with our first example. And what we're going to do is we are going to generate the Maclaurin polynomial. Sorry, not Maclaurin polynomial. We're doing more advanced Maclaurin series for y is equal to sine x, okay? And essentially what we're doing is we're doing something that's very similar to what we did with our power series, right? In our representation of functions as power series. We're going to try to find what is the series representation for y is equal to sine of x using a Maclaurin series. And so thinking about that definition that you just copied down, what we could do is we could find each derivative, plug in our center, and then put it into our series notation. So I'm going to go through this super quickly because we've already done it. But let's say, we have y is equal to sine x, or actually let's call it f of x. Let's just change that y to f of x. That's our first function. When we take the derivative, we know that's going to be positive cosine x. Taking the second derivative, we get negative sine x, and so on and so forth. You should be masters at this by now. Third derivative would then be negative cosine x. And what we're doing is we are plugging in the center. You don't need to write all this down, okay, by the way. We're plugging in the center. So when we plug in 0, we get sine of 0 is, of course, 0. Cosine of 0 is positive 1. Negative sine of 0 is 0. And then we have negative 1. And we know this pattern is going to repeat for on and on, right? So plugging that into our Maclaurin series, what we're going to do is let's just write out the first few terms and see if we can come up with the general form. So we have 0 for the first term, and then we have 1, positive 1, x to the first power, divided by 1 factorial. It's the first derivative, x to the first, divided by 1 factorial. We'd be adding 0x squared, and then we go to minus x cubed, and we're dividing that by 3 factorial, all right? Then we skip over x to the fourth, we go back to positive, it's an alternating series. We can see that the next one would be x to the fifth, we'd be dividing that by 5 factorial. You can probably guess the next one is minus x to the seventh over 7 factorial. And this is going to go on and on and on. So what does our nth term look like? Well, what we're doing here is each of our exponents are odd numbers. So how can we represent an odd number as an exponent? We'd be taking x to the 2n plus 1, right? We need this to be an alternating series, so we're going to add in our negative 1 to the nth power. And then what's in our denominator? Well, it's the same factorial as whatever your exponent is. So we have 2n plus 1 factorial. Fantastic, and this goes on and on and on. So what we have just determined is that our series, our Maclaurin series for y is equal to sine x, is we start at n equals 0 going to infinity, and then we're just going to plug in this general form that we have. So the negative 1 to the nth power x to the 2n plus 1, all divided by 2n plus 1 factorial. Okay, great. All right, so now what we're going to do is we're going to find, just like what we did with our 1 over 1 minus x and all of the problems that we've been doing over the past couple of days, we can find where this series converges. And how do we do that? Well, we're going to use the ratio test. So let's take a moment to do that. I'm going to erase this little bit right here. All right, so applying our ratio test, we have the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. So we're going to replace n with n plus 1. So we have negative 1 to the n plus 1 times x to the 2 times n plus 1 plus 1. So that's going to be x to the 2n plus 3, right? Yeah, don't get that exponent wrong. And then we're dividing that by 2n plus 3 factorial, and we're multiplying by the reciprocal. So we have 2n plus 1 factorial, all divided by negative 1 to the nth power times x to the 2n plus 1. And we do some canceling. So let's see what's going to cancel out. So we can cancel out our negative 1 to the nth powers because we are in absolute values. Our x to the 2n's will both cancel. Then we have x cubed divided by x to the first power. So that's going to cancel out this whole thing from the denominator, and we'll be left with just x squared, right? We have 2n plus 1 factorial. That is smaller than 2n plus 3 factorial. So I'm going to write out 2n plus 3 factorial as 2n plus 3 times 2n plus 2 times 2n plus 1 factorial. And what's nice about that? Our 2n plus 1's factorials cancel out. Okay, guys, so what does this limit equal to? So what we can see is that in our, well, let me rewrite it one more step actually to make it a little bit easier to see. So we have the limit as n approaches infinity of the absolute value of x squared over 2n plus 3 and 2n plus 2 remain. Okay, what does this limit equal to? Hopefully in your mind you just said 0. 0, thinking about our end behavior rules, right? Lots of parentheses there, which this is always less than 1. So what does that mean about our interval of convergence? That means that our interval of convergence goes from negative infinity to positive infinity. Okay, so what we've just done is we've created this Maclaurin series for y is equal to sine x. Okay, and we could do this for any function, going through that process of finding all of our derivatives, trying to come up with the nth term, the general formula, and plugging it into our summation notation, right, into that sigma. But wouldn't it be nice if there was an easier way to do these problems, some sort of shortcuts? Well, it would be, and surprise, there are some shortcuts. So on this next slide, I have taken this from page 674 in your textbook. And what you'll see here are 5 different series that is your goal to memorize, okay? So you'll see here on the left side, the functions. So e to the x is the first one. You don't need to write out all of this. This is in your textbook, like I said. But your goal is to memorize that e to the x we can write as x to the n over n factorial when we put that into sigma. So that's our Maclaurin series for e to the x, okay? It's how we're representing the function e to the x as a series. That's the goal of our Taylor and Maclaurin series, okay? So what you'll see on the bottom, we have 1 over 1 minus x. That's what we've been doing the past couple of days. We've been taking series that look very familiar to that. Well, now we're adding e to the x, sine x, cosine x, and arctangent. So that way we can represent series that look very similar to these. Okay, that's the whole goal. And on the right side of this page, you'll see where they are converging. Okay, so I'm going to have you pause the video here, copy those down, and then we'll apply them. All right. Let's do it. Here we go. So moving on, I'm going to add a page here. Let's do find the Maclaurin series for y is equal to sine of x squared. Okay. So just like when we did, we went from having 1 over 1 minus x, and we looked at how can we write this as sigma, and then we added on to it and we said, well, what if we have 1 over 1 minus x squared? Looks similar, not the exact same, but what we did was we used that basic sigma notation to help us with 1 over 1 minus x squared. And we're going to do the same thing for this one, and that's what a lot of these problems are going to look like, just so you know. So what does y is equal to sine x squared look like? Well, it looks a lot like y is equal to sine x. And how can we represent sine x using sigma notation? Well, we just did it as our example, and you just wrote it down. And it is negative 1 to the nth power x to the 2n plus 1, all divided by 2n plus 1 factorial, right? This is using a shortcut. You should have this memorized. Know that sine is the one with the odd exponents, okay? Odd exponents and odd factorials. So if we are going to take sine x and use it to help us to write sine x squared, what do you think we're going to have to do? Well, hopefully you just thought, I'm going to replace x with x squared. That's exactly what we're going to do. So for sine of x squared, we're going to take that same sigma notation that we have from 0 to infinity. We're going to keep the negative 1 to the nth power. And then instead of having x to the 2n plus 1, we're going to have x squared raised to the 2n plus 1. All right. And then we're still keeping that same factorial. So all that we changed was the x squared. So simplifying this out, let's make it a little bit nicer to see. We have negative 1 to the nth power, and that x squared to the 2n plus 1 factor to it, power to a power is multiplication. So we have x to the 4n plus 2. And that is all divided by 2n plus 1 factorial. All right, let's write out the first 4 terms of this just so that we can see what this looks like. So for sine of x squared, we know that that's equal to our first term. We'd be plugging in n is equal to 0. When we plug in n is equal to 0, we have negative 1 to the 0th power. That's going to be positive 1. X to the 0 plus 2, that's x squared. And that is divided by 1 factorial. Great. What about when n is equal to 1? Well, we'd have negative 1 to the first power. That's going to mean that we have subtraction. X to the 4 times 1, x to the 4th plus 2 would be x to the 6th power. And that is all divided by 2 plus 1, 3 factorial. Okay, what comes next? Negative 1 squared would give us a positive number. We have x to the 4 times 2 would be 8, plus 2 would be x to the 10th power, all divided by, this is n is equal to 2. So 2 times 2 is 4, plus 1 is 5 factorial. Oh my goodness, do you see what's happening here? And if you don't, that's okay. Stick with me. What if we plug in n is equal to 3? We have negative 1 to the 3rd power. That's why I have this minus sign here. X to the 4 times 3 would be 12, plus 2 would be x to the 14th power. All divided by 2 times 3 is 6, plus 1 is 7 factorial, and that's going to continue on. Okay, what do you notice? Well, hopefully you notice that this looks exactly like sine x, but all of the exponents have all been multiplied by 2 because x was replaced with x squared. Okay, so that was the goal here. We took something that looked familiar to sine of x squared, replace that x with x squared, and tried to figure out what our new sigma was. Let's do one more example together. And that is, so this will be example 3. Let's do y is equal to e to the 4x. And we'll do a Maclaurin series for this one as well. Well, what does y is equal to e to the 4x look similar to? Looks similar to y is equal to e to the x. And what is e to the x in sigma notation? Well, it is the series n equals 0 to infinity of x to the n over n factorial. So what are we going to do? What we're going to do is we're just going to replace x with 4x in our sigma notation. So we end up with the series from n equals 0 to infinity of 4x to the n over n factorial. So we used a similar series to get to the series that we wanted to get to. All right, we will practice a lot more of this in class. Thank you for watching, and I'll see you in class.